Welcome to the group exhibit Hydrogen, Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Buarkas. Please have a seat, join us for the next presentation, have a drink, have a coffee, it's all for free. I'm very much looking forward to the next presentation regarding hydrogen in a sustainable energy system, a combination of storage, medium and fuel. Please welcome with me on stage the Deputy Chairman of the Deutscher Wasserstoff und Brennstoffzellen Verband, Dr. Johannes Töpler.
Okay. Thank you very much for the kind introduction. I would like to tell you something about hydrogen in a sustainable energy system, a combination of storage and medium and fuel. And as you see here in the first figure, our old it doesn't work. Our old energies, oil, natural gas and coal, will decrease by resources, and we need in future other renewable and sustainable energy systems, and we have to introduce them before the decrease of availability because or due to the climate change and natural damages. We have wind, photovoltaic, solar thermal energy, biomass, thermal heat, and so on. That are the primary energy systems of future. And if we put this figure in another color, you see here the old energies, the conventional energies, are in general so that the energy is stored in matter. Future energies will be transferred from wind, from solar energy into electricity in the first step. And electricity is the first energy which can be used industrially. That means that we have a strategic transfer from a fuel-based energy system to an electricity-based energy system. In this system, we have to produce electricity. In this system, we have electricity, and we have to transfer in the first step the electricity to fuels. That's the first strategic difference from one energy system to the next one. And another one is the availability. If energy is contained in matter, it is available everywhere and everywhen. But for example, in wind energy, demonstrated here, and in solar energy, we have fluctuations. And in the first measurement, the fluctuation of wind energy was powered several years ago in the Aeon grid. And you see here the fluctuations. And in Germany, we have the legislation to increase the wind power by a factor of 3 till 2020. And if we calculate this, then it is the same fluctuation, but with the wind power as it will be available in 2020. And in the next curve, we have the vertical load. That's the fluctuation of the load in the network. And you see here the differences. In this time, the supply cannot be satisfied by demand. And in this time, the supply outreaches the demand by far. That means we have no parallel situation between demand and supply. And what we need is storage in between. And the storage can be used in the following way. From electricity, for example, from wind or from photovoltaics, we can use electricity in the electrical grid, and this can be used in household and industry in the same time. But if we have not enough energy in the wind, we have used additional storage systems. There are different storage systems, but I will demonstrate it in the first demonstration by hydrogen. The first step is to make hydrogen by electrolysis. You can use hydrogen in the filling station for electrically driven cars with fuel cell, as in the same way as you can use the direct electricity by battery-driven electric cars. And you can store this hydrogen in big storage systems like caverns. You can withdraw the hydrogen for filling station or other applications, for example, in households. You can, in this situation, you can use the hydrogen directly or inclusively methanization, for example, by synthetic natural gas. That's another option, but I will show you how it works and with which efficiencies. And after this storage, you can stabilize the network, the electric network, by re-electrification of hydrogen by turbines or fuel cells. That means you have here a closed energy system for a continuous or a demand-orientated supply of households. And you can use the electric naturally, and on the other hand, if you need, for example, heat, as final energy use, you can use the energy via a gaseous grid. You have here an electric grid and a gaseous grid in combination by this storage. And the next question is how big a storage system must be. And in the first step, we have in Germany available pumping storage systems with energy storage capacity of around about 5 gigawatt hours and an electric power of round about 1 gigawatt hour. And this is the storage area which demonstrate the time which can be needed and the power. In the same way, we have available adiabatic compressed air systems. Both pumping system and adiabatic compressed air systems are use of potential energy. And the adiabatic systems have round about 23 gigawatt hours capacity of energy and round about 1 to 2 gigawatt for electric power. On the other hand, hydrogen is a chemical energy carrier, not potential energy. It's a chemical energy carrier with a reaction energy from hydrogen to water. And in the case of hydrogen, a big cavern has a storage capacity of around about 1,300 gigawatt hours or 1.3 terawatt hours with a power of several gigawatt. That means the storage capacity in a case of a chemical energy carrier, in this case hydrogen, it's the easiest chemical energy carrier, is very, very big. And if we have no wind or less wind for a long time of several days or a week, we can store the energy for industrial or household application for several days. And that's what we need by the fluctuations of natural primary energies. And here you have a demonstration for the energy density per cubic meter. Hydrogen has an energy density of around about 300 kilowatt hours per cubic meter with a compression of around about 120 bars. And if you subtract the efficiencies, then the reversible energy density of hydrogen is around about 170 kilowatt hours per cubic meter. In adiabatic compressed air systems with around about 20 bar pressure difference, we have a density of 2.4 kilowatt hours per cubic meter. And in the case of pumped hydro systems with 300 meter, we have around about 0.7. The difference results from the fact that here is potential energy, here is chemical energy. That means, in a consequence, hydrogen makes renewable primary energy ready for basic power supply, and it makes the energy transition affordable because you can use basic power supply. And the next step is to use hydrogen, for example, in mobility. And the best way to use hydrogen for mobility is a fuel cell. I think everybody of you knows this. And hydrogen is stored in general today in general technical applications by storage vessels. The electricity is produced by fuel cells. And here you have the electric engine. And every fuel cell car has a subsidiary system by a battery for the rewinning of braking energy or for heating the car. And one of the first companies who made these cars were Daimler. They started several tens of years ago. And one of the last one is the B-class. And this car was constructed, fabricated and approved under serial conditions. Then it was tested by a turn in 125 days around the world by 30,000 kilometers. Daimler wanted to demonstrate the serial application. The next step will be a new car. It was not presented in public, but 2 years ago it was the engine block with fuel cell and fuel cell system was shown here at the Hannover Fair, and the car will be introduced in the end of this year. Other companies, for example Toyota, are a little bit quicker. Toyota has the Mirai just on the market with a similar packaging like the Daimler B-Class. It's a little bit similar with 2 storage tanks, with battery, with fuel cell, with electric engine. The packaging is nearly similar. And now let me say some words with respect to battery-driven cars. For example, if you have a gasoline or diesel car, you have to take with you fuel, and you use the oxygen which you need for burning from atmosphere, and you release carbon dioxide and water vapor from exhaust into the atmosphere. What you have to take with you is gasoline or diesel. In the case of a hydrogen-driven electric vehicle, you have to take with you hydrogen, and oxygen is withdrawn from atmosphere, and water vapor is released after the reaction. You have to take with you hydrogen. In the case of a battery-driven vehicle, you have the reaction of the anode. This is one example for a lithium battery. You have to take for each electron, here is the electron output from cathode, here is the electron input at the anode side. You have to take for each electron a molecule of lithium carbide, and at the cathode and at the anode a molecule of lithium manganese. At the anode, for each electron, a very heavy molecule. And if you want to go big ranges, for example a doubled range, you have to take a big storage system. In the case of a gasoline vehicle, you have a bigger storage system in the case of the hydrogen car, and you have a very big and heavy battery in the case of a battery-driven car. The battery has a very, very high efficiency, higher than the fuel cell. But on the other hand, you need additional energy to operate and to transport the battery. And I told you that in general, a battery is additionally used in a fuel cell car. The reason is the following. you can take the electric engine as generator if you want to brake, and this additional electric energy from the generator can be used in the battery so that you have a recovery of braking energy. On the other hand, additionally, if you have a battery-driven car and you want to heat your car in winter, you lose range. You have less kilometers available. In the case of a fuel cell-driven cars, you can use the fuel cell for preheating the car before driving, because you can operate the fuel cell, you put the electricity in the battery and you heat the car before you drive. And when driving, you take the electricity from both, from battery and fuel cell, and and the battery afterwards is empty, and you can refill it in the next operating module without losing propulsion energy. Several years ago, the battery companies, car manufacturing companies, and a lot of companies in Europe have investigated where have battery-driven electric cars advantages and where fuel cell cars. And they found altogether in a European project that in the compact class with low ranges, around about less than 10,000 kilometers per year, and medium classes in this range, in this case have battery vehicles more advantages, and in the case of big cars and big ranges per year, the fuel cell vehicles are hybridized with battery, but generally operated with fuel cells. And in the last time we heard something about improvements with batteries, but this means that maybe this line can be a little bit shifted in this direction, but not more. And that's a case which we may have today. And I told you another thing. I told you that even if you have hydrogen, you can make synthetical natural gas from it by the so-called Sabatier process, and you can use conventional natural gas vehicles. But in this case, you have to look a little bit on the efficiency. A fuel cell has a typical efficiency curve like this. That means at low load, for example, in a general operation range of a passenger car or in the general operation range of a bus, you have very high efficiencies in the case of fuel cell. And in this operation range, you have low efficiencies for a diesel or for a gasoline car. That means for passenger cars, bus, trucks, the hydrogen operation with fuel cell have high efficiencies. And if you have hydrogen and you want to produce from hydrogen synthetic natural gas, the best way to operate it is with cars which are running mainly at very high power density. That are, for example, trucks or long-range buses. These are urban buses, and here are long-range buses. In this operation range, conventional cars have similar efficiencies like in comparison to fuel cell cars in this operation range. And sometimes some people have the opinion, if at the early beginning wind energy is available in a surplus, it doesn't cost anything. And if it costs anything, then the efficiency doesn't matter so much. But on the other hand, if you compare both paths, producing hydrogen via electricity, compressing hydrogen, and using hydrogen with high efficiency for the propulsion system of a car, you have a final efficiency over the whole process of around about 29%. And if you take, in this case, from hydrogen, the Sabatier process with producing synthetic natural gas and use it with less efficiency in an internal combustion engine, a gaseous engine. We have here an efficiency of round about 22%, so that finally in the whole chain you have 12. If you consider the price, which is 0 at the early beginning, then at the end the price doesn't matter. But an energy specialist calculates generally from the opposite direction. I need the energy for propulsion at the wheel of a car. And if I calculate the efficiencies back, then I found how big a wind energy system or a photovoltaic system must be in order one energy unit at the end. That means I have much bigger investment cost for the size of the beginning system, wind or photovoltaics. That means the efficiency of the fuel cell is the main difference and the main advantage for operating a fuel cell car. And if you want, you can calculate the differences between different propulsion systems yourself in internet by the system OptiResource, which was operated and founded from Daimler in cooperation with several universities. If you look in the Google by OptiResource and Daimler, you will find it. You have even an English description or a German one, and you can use the efficiencies and the carbon dioxide emissions for each energy source, for each fuel, hydrogen, electric energy, for example, batteries, and for each type of cars and propulsion system. Here you see, for example, pressurized gas. In the case of hydrogen, and here you see the result for the energy change we have chosen in the case of fuel consumption in relation to liters of gasoline, the carbon dioxide emission for the car and for the system, and you can compare different systems. Maybe you need some tests to do it, but you can calculate yourself. And one of my last figures, there are a lot of possibilities to use hydrogen, not only for stabilizing the electric grid, but for other types of mobility. Here you see the first tests at the University of Birmingham to construct a locomotive. It's the first test. The last one is a final train which will be operated commercially at the end of this year. You can see some models at some booths. We will have in Germany the first hydrogen-driven train exactly at the end of this year. The consequences: hydrogen introduces renewable energies into mobility. It enables electric vehicles to reach long distances and short filling times, and it makes mobility carbon dioxide free. And now I thank for your attention, and maybe we see it or we meet each other at the internet page of our association.
Thank you very much, Dr. Johannes Töpler. Looking at the time, we have not so much time for questions. Are there any right now? Otherwise, I would like to ask the questions later on. So we can continue with the next presentation. Thank you very much. If you have further questions, go by the booth E63. He will be there and be available for questions or discussions. We will continue in a minute with the next presentation regarding hydrogen in a sustainable energy system, a combination. Oh, excuse me, that was the one we just had. The next one will be off-grid and backup energy solutions based on direct methanol fuel cell. Please stay with us and have a drink, have a coffee, and see you in a few minutes. Thank you very much.